Hello to all, I am Dr. Alkesh Agrawal, and in this lecture, I'll mainly discuss what is an integrated circuit, how the ICs are classified based on the number of components that they contain, what is logic family, and what are the characteristics of logic family. Here are some reference books that include Digital Design by M. Morris Mano and M. D. Saletti, and Modern Digital Electronics by R. P. Jain. So let us discuss the basic definition of an integrated circuit. It is also abbreviated as IC. So an IC is a small silicon semiconductor crystal, also known as a chip. So this chip contains different electrical components that include transistors, diodes, resistors, and capacitors. These electrical components are being interconnected inside the chip, forms an electronic circuit. Here you can see in figure 1 we have the actual figure of an IC which is of exclusive OR gate 7486, and here you can see the gate diagram of the 7486 IC. You can see you have four exclusive OR gates. So this particular IC is being mounted on plastic package and the connections are being welded out as external pins. So here you can see a groove, and the first pin below this groove is the first pin. So this is the first, second, third, fourth, fifth, sixth, seventh from left to right, and then on the other side the pin numbering starts from right to left. So we have 8, 9, 10, 11, 12, 13, and 14. So you can see in the figure. Now we have the classification of ICs based on the components that they have or that are being fabricated inside the chip. The first is SSI, that is a small scale integration. So this is the first classification of IC, which contains about up to 99 components, electrical components inside the chip. Then another classification is MSI, medium scale integration. So this particular IC contains the electrical components varying from 100 to 999. Third classification is LSI, that is large scale integration, where an IC contains the electrical components varying from 1000 to 9999. And we have VLSI, that is very large scale integration, where the electrical components varies above 10,000. So nowadays we have lakhs of components that can be fabricated in VLSI technology. So now let us discuss what is a logic family. So initially we discussed about an IC, the classification of IC. So a logic family, it is a group of compatible IC that has same logic levels and supply voltages in order to perform various logical as well as arithmetic operations fabricated using a specific configuration, and that is being termed as logic family. So we have a broader classification of logic families as bipolar logic families, which are shown in table 2, and unipolar logic families shown in table 3. So in bipolar logic families we have some important logic families that are RTL, which is resistor transistor logic, DTL, diode transistor logic, TTL, transistor logic, I2L, integrated injection logic, HTL, high threshold logic, DCTL, direct coupled transistor logic, ECL, emitter coupled logic. So another, we have unipolar logic families, so that are based on metal oxide semiconductor logic. So we have PMOS. So this is being P-type metal oxide semiconductor logic, NMOS, N-type metal oxide semiconductor logic, CMOS, complementary metal oxide semiconductor logic. So we have logic family. What is logic family? It is a group of compatible ICs that work on the same logic levels and supply voltages to perform arithmetic and logical operations. We have two kinds of logic families. One is based on bipolar logic families and one is based on unipolar logic families. So we have certain standard examples of logic families tabulated in table 2 and table 3. Now we discuss some characteristics of logic family. So in table 4 we have depicted some characteristics that are speed of operation, power dissipation, figure of merit, fan out, noise immunity, operating temperature, and power supply requirements. So we'll discuss one by one in subsequent slides. So first is speed of operation. You can see here we have this is the input signal. So input signal, when we get input signal, it builds up slowly. We have a mark of 50% and then it stabilizes and then it degrades. And this is the output response, where output response is again starts building up, goes to 50%, stabilizes, and then again comes back to the initial position. So we define propagation delay. You have seen here, this is the 50% where the input logic is building up, and this is the 50% mark where the output signal is building up. So we have the difference between the two is TPHL, which is defined as propagation delay time from high to low transition. That is, the input signal is building towards high, and output signal is going towards low. So this is the delay, the difference between the two building up of responses, the input response and the output response. Then again here we have the TPLH, which is propagation delay time from low to high transition. That is, the input response is approaching from high to towards low, and the moment it crosses 50%, and here the output response is uh, you know approaching from low to high status, and we have a mark of 50%, and the difference of the two is TPLH. And the propagation delay time is the average value of, that is, transition propagation delay from high to low logic, and propagation delay from low. So this is the average value of propagation delay from time from low to high, and propagation delay from high to low logic. So mainly its unit is nanosecond. Then we have power dissipation. So as you can see, whenever any electrical component is being operated, it dissipates power. So that is true for ICs also, because IC contains some electrical components. So this is the amount of power that is being dissipated by an IC. It is being depicted in terms of the current that is being drawn from the supply. So power dissipation is the product of ICC into VCC. That is the current drawn from the supply voltage. Its unit is milliwatt. Another characteristic is figure of merit. That is a combination of propagation delay and power dissipation. So figure of merit is propagation delay, which is measured in nanosecond, and power dissipation, that is measured in milliwatt. Then we have another characteristic as fan out. So here you can see we have a TTL driver or a TTL gate. So what it is written that as a driver, this is a driver and this is a load. We have the same type of TTL gate that are acting as a load, and this is a TTL driver. So a driver gate, it act as a source of current. So the maximum capacity of a TTL gate as a driver is 400 microampere, whereas an individual TTL gate that act as a load, it sinks on an average about 40 microampere of current. So you can see, if you have if you equate both the uh, the the source current as well as the sink current, so you can see with the maximum capacity of 400 microampere, it can drive 10 such gates. How we have calculated for 400 microampere upon 40 microampere. So as such, the figure in this particular figure, the fan out comes out to be 10. So how we define a fan out? This is the number of similar gates that can be driven by a gate. So high fan out is advantageous as it reduces the need of additional drivers to drive more gates. So here one TTL driver can drive 10 similar gates. So again we can discuss how we have calculated. So as a TTL driver gate, it can from this particular gate you can draw about maximum 400 microampere of current, whereas TTL, when it acts as a load, it requires a minimum of 40 microampere of current to get operated. So with the maximum capacity of 400 microampere, one TTL driver gate can, operate 10 such similar gates. So we have a fan out value of 10. Then noise immunity. So here in this figure we have shown, we have output voltage profile of TTL under low logic, and we have input voltage profile of TTL as again low logic. So here you can see in the output voltage profile, it varies from 0 to zero point 0.4 volt. So that is, any voltage between 0 to zero point 0.4 volt, it will remain as low logic voltage uh, for the TTL output. But under similar conditions of low logic, the input voltage profile varies from 0 to zero point 0.8 volt. So what happens if this output voltage is being given to the input as a low logic? So with the addition of noise, in zero point 0.4 volt, the maximum noise that can be added is zero point 0.4 volt. So still from zero point 0.4 volt it will go to zero point 0.8 volt and it will remain in the low logic. So under such conditions the noise immunity is zero point 0.4 volt. So how we have calculated? We have 0.8 minus zero point 0.4 is 0.4 volt. So this noise immunity over here is 0.4 volt. Then we have operating temperature. So this particular characteristic depends upon the extreme temperature range in which an IC functions properly. So in this table it has shown that for consumer and industrial applications, the operating temperature ranges from 0 to 70 degrees centigrade, whereas for defense application it varies from minus 55 degrees centigrade to 125 degree centigrade. Then power supply requirements. So the supply voltages and the amount of power required when I see are very important characteristics that are required to select the proper power supply. So here in this table we have some power supply requirements for different IC series. So for 74 series TTL ICs, it varies from 4.75 to 5.25 volts. That is, if we have 74 TTL ICs, so they are operative from 4.75 to 5.25 volt. If we have CD 4000 series in CMOS, though they are operative from between 3 to 18 volts, and if we have 74C00 series in CMOS, they are operative from 3 to 15 volts. So these are standard power supply requirements for different IC series. Thank you.